The smallest unit of execution in GPU is threads, but that's not meaningful. GPUs execute in terms of warps rather than threads. Warp is basically 32 threads running a single instruction in parallel. The tiles are smaller than actual M and K dimension. Instead of computing a single element, we basically compute a tile or outer two loop is embarrassingly parallel. Like you can distribute it to cores on CPUs or SMs on GPUs. The thing is, then you have to pay the communication cost. Multiple warps can actually communicate very fast, and multiple warps can use the shared memory. So that's the main concept. Okay, so and let's look at what tiling is. So now, instead of computing a single element, we basically compute a tile of element. In this case, the tile size is tile m cross tile n. PE over here is the processing element. That means every PE can run in parallel and compute tiles. So in this case, each PE is actually computing tile m cross tile n, and you are going across the rows of A and columns of B in forms of tiles of K. So the key insight is the outer two loop is embarrassingly parallel. Like you can distribute it to cores on CPUs or SMs on GPUs, and we'll take a look at like what SM means in terms of GPUs. And the inner tile K is basically a reduction tile, so it is serial. You can distribute it, but the thing is, then you have to pay the communication cost. So in this case, we are just doing a serial reduction across the K dimension. Do you have any questions over here, or? Yeah, the tiles are smaller than actual M and K dimension. Yeah. Okay, so the three loop tile Matmul actually looks like you have tile M, tile N, tile K, and then you are actually doing a Matmul there. So that is basically what that is basically this particular thing that's happening, but in a smaller tile. So yeah. Yeah. Now we'll try to take a look at like what is present in GPUs. So the smallest unit of execution in GPU is threads, but that's not meaningful because GPUs execute in terms of warps rather than threads. So and a warp is basically 32 threads running a single instruction in parallel in a lockstep. So and then and multiple warps actually run in a thread block. So the hierarchy is basically thread is the smallest unit of execution. Then you have warps and thread blocks, but you have to think in terms of warps. If you do conditional in terms of thread, you'll get warp divergence. So yeah, execute in terms of warp. That's the basic thing about this. And I think I can take questions over here, like if anyone has. That's hardware defined. In AMD, it can be 32 and 64. So I think they have RDNA and CDNA thing in AMD, and now they are also converging to 32 right now. So a warp is basically it is basically hardware constraint. Yeah.
If we have warps, then why do we need a CTA?
So multiple warps can actually communicate very fast, and that's why you need CTA. And multiple warps can use the shared memory. So the thing is, in a CTA, basically in a thread block, every warp can utilize the shared memory that's present over there. So that's the main concept.
So we would be doing reduction over CTA, right?
We will be doing reduction over CTAs. Yes. Yes. So basically, we'll distribute the M and N tile across SMs, and then we'll distribute and reduce in a single CTA. You're right. Yeah. So and like I'll try to map what we have seen in the next slide. So you have a SM, which runs the entire thread blocks CTA. And then you have 4 warp schedulers, which actually executes a warp. So in a SM, 4 warps can run in parallel. And they all share a very fast memory called shared memory or L1 cache. So you can program it is programmer managed memory. You can make it as a L1 cache, or you can make it as shared memory, whatever you want. Like, how do you want to program it? Outside that, and you have, like, in Nvidia GPU in Blackwell, you have hundreds of these. So around 148 in Blackwell B200s. So you have like massive level of parallelism when you have like in a GPU. And then all the SMs share L2 cache, which is shared across SMs. And then you have global memory, that is a system-wide memory on Nvidia GPU. So yeah. So now we'll try to take a look at what Volta introduced. You have a question? Yeah.
What is the hierarchy for SLMB shared memory, L2 cache, and then SPM?
I see. So shared memory, so registers are very fast. Shared memory is on chip, that's also very fast. L2 is shared across SMs, that's fast, but not, that can be thought of as off-chip memory, that's not that fast. And then you have global HBM, which is very slow.
What about tensor memory and register?
Tensor memory will come in Blackwell. So tensor memory and shared memory, you can think of it as working at the same speed. Yeah. Yeah. So we are trying to take a look at like what the tile Matmul look like. So you had M and N tiles, which will be distributed across SM. So you don't have to care about that. You have to care about the inner tile, which runs on a single SM. And Volta introduced one operator, which is MMA.sync, which can do 16 cross 16 cross 16 Matmul, not in a single cycle, but as a single operation. So, and it's very fast. So this particular operation, A tile M tile N multiplied by B, can be done with a single MMA if the tile M, tile N, and tile K sizes are 16 in this case. So basically now you do load, compute, and store. Compute is done by tensor core. Problem over here is, I can take questions first and then maybe, okay. So the problem over here is when the load is happening from HBM to shared memory to registers, the compute cannot function during that time. And when the compute is happening, the store cannot happen. So all of these are basically synchronous in a way. And that's what we don't want. We want the tensor cores to actually work all of the time. So we'll see in the next slide that this is basically the serialization problem that Volta gave. And once you have load, the MMA cannot function during that time. And basically so this diagram actually tells you are iterating over all the tile Ks, and then you are basically storing at the very end. When the load is happening, you can see the MMA is not functioning. So that was the major problem with Volta. No, you cannot. That's the problem over here. So when you are fetching, the compute units cannot work during that time. Yeah. It's a limitation of Volta GPU. That was like 8 years back, I guess. Yeah. So they introduced something which is very novel, the tensor cores. But the problem was that they were not able to use tensor cores all the time. Yeah. So we are directly jumping to Hopper, not Ampere, because Ampere introduced asynchronous, like what you talked about right now. Like once the load is happening, the compute should happen. And Ampere exactly introduced that with async thing. But I'm skipping Ampere and directly moving to Hopper. Hopper introduced two primitives. One was the tensor memory accelerator, and one was the warp group MMA. And these both are asynchronous operation. So when one happens, by asynchronous, it means when one happens, the other can function freely. So the thing was, let's first discuss about TMA. The TMA is basically it basically loads from HBM to shared memory, and it fires and forgets. Uh, uh, and basically, it can load and it can even store with this thing. So it basically stores from shared memory to HBM, and it fires and forgets. And WGMMA is you have 4 warps running in parallel to execute a bigger tensor core, and that also happens happens asynchronously. The other part is that it can directly fetch data from shared memory and not registers. So that's also like you can directly load from SMEM and then issue a WGMMA and forget about things. So, any questions over here?
Does Blackwell has warp specialization?
I mean, warp specialization can be thought of as a concept. It's not related to any hardware. You can do warp specialization on Ampere or Volta or any hardware.
Okay, and if we are talking about bank conflicts, how they are evolving, how we are resolving this in the
So
older
I didn't
architecture.
talk about bank. So I didn't talk about bank conflicts. The thing is, TMA introduces something called as swizzling, which removes the bank conflicts when you are loading from HBM to shared memory.
Thank you.
Yeah.
So, so does TMA also do tiling? I mean, like in the DMA, kind of like, from linear to tile and all, or by using this specific.
Yeah. Yeah. Basically,
Okay. So it's a 2D format inside. I mean, it doesn't go linearly.
it is from 2D to 5D format. So you can tell it what shapes to actually fetch from HBM. It will do all the strides calculation, the shapes calculation, and everything for you.
Okay. And is there any I mean hardware cache that is coming into picture, or is it all software managed?
No, the TMA is hardware. It's a new hardware that does this.
Okay. Right. So I mean, it's basically the hardware itself does this whistling, and we just I mean, from the software, do we have to do any what do you call that movement data movement to get it into this format, or it's
Yeah,
not
you
possible?
have to provide the shape stride, not the stride, the shapes, coordinate, and the swizzling, and it will do it for you.
Okay.
Yeah.
Hi, Prashant. Just because we are just introducing the architecture, like, can you also explain like how CUDA stream is related like with this architecture?
CUDA streams.
Yeah.
I think CUDA streams is a concept as in you can have multiple streams and then you can execute things in multiple streams, right? Like it is a
Wait.
concept like present in every hardware architecture, every GPU of Nvidia, I guess. It's a software concept, I guess. It's not a hardware concept.
Okay. So basically, it's an implementation where we can leverage TMA more exhaustively.
Yeah.
Okay.
Yeah.
Yeah, so I was asking, so the tensor core is a different unit and the 4 walk groups, or is the 4 walk groups altogether are known as a tensor core? I'm asking where the computation is happening.
Oh, yeah. Tensor cores are different. It resides in the warp group, but these are different hardware units that reside in the warp group.
Okay.
Yeah.
And its length is, so for a MMA, which is 16 and 16 and 16, it is able to take 2 kinds of 16 cross 16 and produce a 16 cross 16.
Yeah.
Okay.
Yeah.
And the warps are just fetching the memory and feeding it into the tensor.
Yeah, so the WAPs are basically looking into the shared memory and then directly doing your Matmul.
Okay.
Yeah. The problem over here is the store is happening and the accumulation is happening in the registers. And we'll take a look at like that basically is a problem of Hopper. Okay, I'll move to next slide. Yeah.
So TMM transfers memory from local memory to shared memory.
Yeah.
Then threads are used to transfer from shared memory to the register, right?
Then threads are
Threads are used to transfer memory from shared memory to register.
no. The tensor code directly fetches from the shared memory. So I mean, they basically you can think of it as all the WAPs coordinate at that particular time. I alluded to one fact that Nvidia has two proxies. One is the generic proxy and one is the async proxy. And these are like, so these are running in the async proxy domain. So your generic proxy can do anything during that time. And the generic proxy is basically your threads that you're talking about, the normal threads, yeah. But that's basically like going into PTS. I didn't have that time, so that's why I didn't do, yeah. So yeah, I'll move to next slide. Yeah, so someone talked to me about WAP specialization. So you have this async thing. How do you actually run it is a major thing. So the problem is like who should use the overlap? Can you trust the compiler to do the overlap for you? I don't think so, because Triton recently moved to Gluon, where they give the power to the user to do WAP specialization and these kind of stuff. So the problem over here is everything in a WAP runs sequentially. So so the thing is, once you fire an async MMA and then doing a TMA load for the next tile, it will be blocked until the MMA is computed. So what you want to do is you create different, you specialize WAPs based on their roles. In this case, you are specializing two roles. One is the producer. The producer is only responsible for doing TMA loads, and the consumer is responsible for doing MMAs. That's it. And basically, this makes this particular hardware, when you WAP specialize it, it makes it out of order. CPUs do it for you because they have something called as reorder buffer, and they do everything for you. So with WAP specialization, you actually make it out of order processor. If the compilers are smart, WAP specialization won't come. And you can read this blog. This is a very good blog on WAP specialization. Like I had this in mind, like WAP specialization is a hardware concept. It's actually the limitation of compiler that's not able to WAP specialize your things. So yeah, so once you have this, you can think of your producer and consumer. You have divided in two parts, and then your K loop is actually loading tiles through TMA. And when the TMA is have loaded the first tile, you do a WAP group MMA on that, right? And then you basically do it until the last part. The epilogue is basically the problem happens because after end, it basically transfers everything to registers. And once it transfers to registers, there is no asynchrony over there because now you have moved from async domain to generic proxy, basic async proxy to generic proxy, and then your basically computation halts over there. So, and you'll see that in the prologue and epilogue, you have still some space to do something, right? Yeah. So this is, so basically what we want to do now is remove all the bottlenecks, as in like remove the epilogue and that halt that is happening in epilogue, and fill these tiles in the prologue and epilogue with some computation. So yeah.
This could be a thing in a
Single CTA. Single CTA with two producer and consumer, basically. And producer is like 128 threads you assign for producer and 128 threads for consumer, and then they run parallelly. Yeah. So in this case, I didn't tell the tile sizes. When you have four, Hopper introduced warp group MMA, which goes up to 128 cross 64 cross 256. So MKN. So M is 128, K is 64, and N is 256. So it's like, yeah. So, and now moving back, we'll try to take a look at grid stride loops. So the thing over there, so let's take an example in which you have 16 elements, and let's say the GPU has 4 SMs, and you want to schedule this work. So there are two ways to schedule this work. One is that you launch a grid with 16 blocks and do one compute per block, and the hardware will manage it for you. But there is another way to do it, the grid stride block. You know that the number of SMs is 4, so you know the number of parallel blocks that can run is 4. You put the grid size to be 4, and then every block will do more work. In that case, you have done it statically, like you know which block is doing what kind of work. So in this case, you'll see in the diagram that this 16 elements is divided into these blocks, and you can see SM0 is actually working on 0, 4, 8, 12, and these kind of things. So this is basically the idea behind persistent kernels. Any questions over here? I'll just drink some water. Yeah.
We do stride so that GPU can, SM can access the memory in parallel. If we don't do this, right, it will access the memory sequentially. But we have to do this stride so that it will actually go it.
Actually, this is doing a wrong thing. The thing is that we are talking about memory coalescing, right? Like you want to do coalesced access. So you want the SM0 to load 0, 1, 2, 3, and SM2 to load 4 elements at a time. This is just a concept of showing that there's two ways of running a kernel with full speed. One is hardware managed, and one is managed by you. Yeah.
So the technique is basically getting rid of compute intensive.
No, I mean the thing is, no. The thing is, this is both of them will run at the same speed, but the problem happens when you have asynchrony involved. So yeah. Yeah, let's take a look at next. So yeah, so this will basically verify like what's happening right now. So these are M cross N tiles that you want to schedule to 3 SMs, right? And let's say you schedule a tile. The problem is when you don't have the persistent kernels, which is the grid stride loop, you have these bubbles introduced by the hardware. So, and that's what we don't want in case of asynchronous pipeline. So what we want is you launch the kernel once, and then you basically loop over that thing. And now you're introducing the bubbles just once in the pipeline. This is a very nice video. I have linked it at the bottom. You should watch. So this is the difference between both. And with persistent kernels, what you're trying to do is, let's say this is not a tile 0, this is actually tile 1. You are actually overlapping the consumer with the previous TMA store and the epilogue with the next load, right? So you are basically filling these two gaps when you have a persistent kernel design. But if you don't have the asynchronous pipe, like if you have a synchronous pipeline, this won't help you because so it helps only in asynchrony that's why persistent kernels wasn't involved, wasn't introduced in Ampere. So so now let's take a look at like how to basically remove that particular register to SMEM halt. So the thing is, this is very common nowadays. Like if you read papers like Flash Attention 3 or 4, you'll find the ping-pong scheduling is like, that's what they do. So instead of launching one producer and one consumer, you launch a single producer, but 2 consumers. And then once the consumer 1 is actually doing the epilogue, you can fire a WGMMA. And then you ping-pong between that. So if the consumer 1 is doing the epilogue, you are doing matrix multiplication, and if the consumer 1 is doing WGMMA, you are doing the epilogue. The problem that ping-pong scheduling introduces is basically how do you manage all these consumers, and you have to like introduce barriers at the right places and everything. So yeah. Any questions over here? So this is basically, if you do persistent plus ping-pong scheduling on Hopper, you'll find that the Matmul gives you the best performance. Yeah.
So I understand what is happening here.
Yeah.
But you had a previous diagram where you said that instead of having bubble, you like 2 blocks. Can you go back to that slide?
This one.
No. Yeah, this
Yeah.
one.
Yeah.
So what are the blocks on the left hand side and right hand side? Is it just the WMMA, or is it WMMA plus PMA store, all that combined?
Oh, that particular blocks, red blocks, bubbles that is introduced inside.
Yeah. So the bubbles are loading.
So the bubbles is basically asking the hardware to fetch the next tile for you, or you have statically scheduled it. You know what is the next block that you should work on. So yeah.
So it's loading larger data on the right hand side.
Yeah. So the problem over here is once you have introduced bubbles, the bubble is actually you have to initialize TMA descriptor and everything. So that's the problem over here. Yeah, because yeah. So yeah, so if you do persistent scheduling with ping-pong scheduling, you'll find that this gives you the best performance on Hopper, even for Flash Attention 3 kernel. So yeah.
Why this isn't there like some overhead in for both consumer and as compared to in the previous slide, there was this one epilogue. So there was some overhead.
Yeah. So the problem over here is that you won't be able to do 128 cross 256 WGMMA. You have to do a smaller tile because the register overhead is like too much now. So each of the let's go to basics. So in an SM, there is 65536 registers. So the maximum and the problem over here is each thread is allocated 255 registers. So if you want to utilize the entire register, you should actually launch 256 threads, right? So 256 into 256 is 65536. Ideally, you can do 128 cross 256 and with consumer 1 and consumer 2. The problem that happens is you need registers for other things as well. So that's why, what producer doesn't need any registers. The consumer 1 and consumer 2 are register heavy. So the producer donates register to consumer. So that's the idea behind that.
So is there like
yeah, the trade-off is basically smaller tile sizes. Yeah. So I think with ping-pong, it goes up to 128 cross 192 or 208, the maximum tile that you can compute, the tile M and tile N sizes. Yeah. So yeah, so now let's move to Blackwell. We saw that the registers part was like doing the ping-pong scheduling was pretty scary. So what Blackwell introduced was two things again. One was the tensor memory. So instead of accumulating in registers that Hopper did, we accumulate in tensor memory, which is again at the same level of granularity as shared memory. So, and the other thing that introduced was tcgen05.mma. Now you don't need like 4 WOPs to actually run that MMA. It separates that and you can launch it with a single thread. But we cannot do that with a single thread. We have to issue a WOP basically to do a tcgen05.mma. A or B comes from shared memory, and the A can come from tmem, and A or B can be in shared memory, and basically it accumulates in tensor memory. So the thing is, now you don't have registers in this pipeline. So it basically decouples into 3 parts. So the thing is, now in case of Blackwell, there are 3 WOP specialized thing. One is the TMA load, the other is the MMA, and the third one is the epilogue. You load, you do MMA, and you store. Everything is synchronous and in, like fully pipelined. And you don't need like 384 registers to do this. You just need like a 1 WOP for TMA load, 1 WOP for tcgen05 MMA, and 1 WOP for epilogue. So this is what Blackwell introduced. Like, it introduced something that was the problem for Hopper. So yeah, yeah, yeah.
For TNA load, tcgen05.mma and epilogue, which one is performing operation? Which one them versus TMA load?
Oh, I see. Okay. So the TMA load is actually loading from global memory to shared memory. Then you have MMA, which directly takes inputs from shared memory and does the MMA. And then it stores in tensor memory in the epilogue. And the problem is that tensor memory is actually, there's one issue with tensor memory is that it is actually subdivided, subpartitioned across all the WOPs, across 4 WOPs. So you need 128 threads for that. And in the epilogue, you basically load from tensor memory to registers, load from tensor memory to registers, put it again in shared memory, and then issue our TMA store over there. So,
Why can't we directly transfer from tensor memory?
there's no hardware instruction for that. I think they will introduce that in Vera. Maybe they should. Okay, there is one more problem with tensor memory, that it only accumulates in F32, and we don't want that. And you cannot do anything in tensor memory. Like, you can only store and fetch results from there, and you cannot compute over that, compute or store over that. So that's again a problem with that. So
The hierarchy of accumulation that you get.
shared memory, yeah. So yeah, and then we have 3 more Blackwell features. The one is 2 CTA MMA. Like, all the things that we were looking up till now was happening on a single CTA. But now Blackwell introduced 2 CTA MMA, where you can actually do a bigger M dimension. Like, you can double the M dimension, and you can do 256 cross 64 MNK tile at once. So this is what Blackwell introduced, the 2 CTA MMA, and they have something called as cluster launch control. Okay, so the problem here was in persistent scheduling was, like, these tiles are statically scheduled, and if you have, let's say, SM1 free, it cannot take steal work from SM0, like the 8 or 12th tile, 8 or 12th element, right? So Blackwell introduced something called as cluster launch control, in which you basically query which tiles, which SM is free, and then you schedule work on that particular SM. So this is very helpful in case of MOEs when you don't know how, like, the router decides where to send the tokens, which experts to send the tokens, and you don't know how many tokens to schedule. Like you don't know about how many tokens each experts will get. So that's very useful in this part, the cluster launch control. You can steal work from one of the SM where you don't have, where it is less compute intensive to other one. And the third one is preferred and fallback cluster. Nvidia gives an option of launching 2 clusters at the same time, and it will perfectly overlap your work. So let's say you have Matmuls, which is actually with a cluster size of 4x4, and you have a smaller Matmul, which is a cluster size of 2x1. It will perfectly overlap it, launching 2 kernels at the same time. So these are a little bit advanced concept, and there is a very good video on this part. So after utilizing all these features of Blackwell, like we have our gem. So this is just on BF16 Matmul. You'll see that in some of the, so this is we are comparing our Matmul with the QDNN, which uses QBLUS, which is the state-of-the-art library from Nvidia. The thing over here is we are beating QBLUS in some of the shapes, which is like pretty good. But the problem happens when we have K very big K. The problem happens is in that case, you need to distribute the K dimension as well across SMs. And we don't use something called a stream K, which actually does this. Yeah. So the best part about this is once you have your own Matmul, you can do any sort of epilogue fusion on top of that. You can mask it, and instead of doing normal loads, you can do a gather load in the prologue. So yeah, and you can understand the hardware better. So this was basically the thing. And if you have any questions over here, I can take it. Yeah.
So what do you mean by coherent BF60 pattern?
So this is our kernel, which is actually written with QDSL. Yeah. Yeah.
So why do you try to write it in
So you cannot write Blackwell kernels with Triton. They don't give you the access to shared memory and warp specialize or something like that. So now they have started to move to something called as Gluon. So we didn't use Triton on that region. On that reason, the other QDSL gives you a very low level power at the PTX level power to control the hardware, and it is moving very fast. You'll see a lot of state-of-the-art kernels. Even Flash Attention 4 was released in QDSL. So, but the problem with QDSL is that that you have to be like you should know the hardware to actually write in QDSL. Oh, okay. So Cutlass and QDSLs are same. It's just that QDSL is a Pythonic version of Cutlass with really less compile times. Yeah. And I think we have Thunder Kittens as well. They are doing really good. And the tile-based abstraction has come, like there's Qtile from Nvidia that doesn't give you that kind of hardware abstraction, but gives a very good performance because they can reason about warp specialization and these kind of things. And I think you are also working on IRI, which is you are working on IRI. Yeah, that basically. So the thing is that everything is managed by them. They give you the state of art performance on AMD. So yeah, so you can try this yourself. So there are a bunch of things present in QDSL, and maybe you can vibe code as well. You can put this slide in and then go to QDSL, say Claude Opus 4.7, and then it can do some stuff. But the thing is, you should know the hardware if you want to get optimal schedules really fast. I have been using Claude a lot, but the thing is that it basically moves in a doom loop really fast, and then it doesn't give you a good kernel. If you know the hardware, you can basically tell Claude to do a lot of stuff for you. So yeah, I mean, if you have any questions, feedback, please let me know. Yeah. Thank you, everyone.